third part of astrophysics is very conceptual. In this part, we're going to talk about HR diagrams. Maybe that they're scientists, I can't remember the names, but they start with H and R. HR diagrams, and basically like different types of stars and like the life of a star, like how a star is formed and how it spends its life and how it's made and how it dies, why it dies out. And it's very conceptual. So let's start off with going over the only equation in this little section is a relationship between luminosity, power, and mass. But before we talk about that relationship, let's talk about the different types of stars. So on this HR diagram, here's the way it's plotted. Luminosity or power, the watts, is measured on the y-axis, and wavelength, or you can also sometimes use temperature, because remember Wien's law, wavelength and temperature are related to each other. You can plot that on the x-axis. And it's generally like there's this trend that goes down this way. Now the units are not labeled here on here, but everything, like most stars, spend the majority of their life, like 90% of their life, on this trend, somewhere on this line. And actually, if I were to point out the sun is like right here. The sun is like somewhere in there. So these stars right here are called main sequence stars, meaning they have a proportion, like they're stable stars. They spend the majority of their life as like young, healthy, youthful stars. Kind of like, teenagers, middle, young adults type of age. They're healthy, they're young, they're active in terms of like an analogy. But here's how you can tell if it's a main sequence star. Its luminosity is proportional to its mass to the 3/5 power, not 3/5, but 3.5 power. So here's an example. If I have these numbers are not relevant because they're so small, because the stars are ridiculously big. But let's say I have a 1 kilogram star. If I take 1 to the 3/5 power, or not 3/5, 3.5 power, I get 1. So the luminosity would also be 1. If I take a 2 kilogram star, its luminosity is going to be 11.3. If I take a 3 kilogram star, take it 3 to the 3.5 power, I get 46.8. So basically, if you notice, it's not going up at a constant rate. It's going up at an exponential rate. And in fact, if I were to plot luminosity versus mass, it would look exponential. Like 1, 2, 11.3, 3, 46.8. And here's kind of the rationale for that. Let's say I had a little itty bitty star here. There's 1 kilogram. It's going to be very, very dim. If I take a star and I triple it, make it 3 kilograms, it's 3 times bigger, it's going to be way, way brighter. Think about if I had like a light bulb that was 3 times the size. It's going to be way brighter to look at that light bulb. You don't even need one that's 3 times the size. There's one in the room that's like a little bit more than, like maybe like 20% larger, and it's like 3 times brighter. Like it's not proportional. It uses this relationship here. But anyway, that's more of a conceptual idea. So let's say you can tell if it's going to be a main sequence star. Now, stars spend most of their life in the main sequence, but they're not there the entire time. So let's go through like the life of a star. So a star is born. Hey, you're the next star. You're the next star. A star is born. No, we'll talk about these types of stars. So how is a star born? Well, basically, it starts off as a collection of dust and particles in space. So you get all this dust and particles scattered throughout space, and they just move around, and then there's a lot of particles and dust in space, and they just kind of meet up. And remember Newton's law of gravitation says Fg equals gmm over r squared. So as those particles get closer together and more dust collects, the mass goes up, the distance gets smaller, and all that force brings them in. It's an attractive force. Gravity pulls them in. And it just keeps growing and growing and growing. As more dust collects, its gravitational force gets bigger because there's more mass. And the radius is going to get smaller because the force is getting bigger and they're attracting each other. So basically, it just takes a long, long time, but the dust just keeps collecting and forms a star. Now, the second thing that happens, when the dust collects, all those atoms in the dust, they're forced together because of gravity. and more dust piles in because of gravity. It's like it's squishing and it becomes really, really dense. And when you have all that pressure and density put together, you produce a lot of energy. And these atoms inside of there go through something called nuclear fusion. So nuclear fusion is when you take atoms and you put them together to make a bigger atom. So a common example is when you take hydrogen and put it together with another hydrogen to make helium. And there's some proton. It's not balanced. We'll go over that in nuclear physics, how to balance this reaction. But two hydrogen, a proton, put together, make two protons. That's helium essentially, with add some neutrons in there. So we can make bigger and bigger elements, and eventually we can make all the elements in the periodic table up to a certain point for the stars. So the stars are actually where most of the elements come from, are from stars. And actually, the most abundant elements in the universe are hydrogen and helium, because that's where most of the life of the star comes from, is by fusing together hydrogen and helium. So, star is born. Basically, you have a collection of dust comes together with gravity, and the dust then fuses together because there's so much gravity, the atoms, and then fusion is a nuclear process that releases energy. So there's radiation. So the star basically looks like this. You have particles coming in because of gravity, put them in, and then they expand because of this nuclear reaction. So it's sending out radiation. So you got gravity pulling in, and an expansion of nuclear pushing it out, reaches an equilibrium point, and it also just keeps growing as it gets, as more dust comes in, it keeps growing. So the star can relatively stay stable, and it's going to stay relatively in this main sequence. Now, the more dust it gets, the bigger the mass is going to be, and the brighter it's going to be. So blue supergiants are, remember, blue is a very, very high energy color, and they're going to be blue because there's very high temperature or low wavelength, and they're going to be big. So they have a lot of power, a lot of luminosity. So it's very, very, very bright stars. They're one of the biggest stars in the sky. Now, what ends up happening after the main sequence? So as time goes on, there's always so many elements, or atoms in the star. There's lots of them, billions upon billions upon billions. I can't even count them. But as these atoms start to fuse into bigger and bigger elements, because first you form helium, then you form lithium, then you form carbon, you form bigger and bigger elements. Iron is actually the death of a star, because iron is the most stable element. It doesn't want to fuse with anything. It's just basically, iron is very stable, and like these smaller elements, they want to grow to become iron, because iron is a very stable element. So once it reaches iron, it's not going to fuse anymore because it's stable. So what ends up happening is once all these atoms come together and start to form iron, they stop fusing. So the nuclear reaction basically started to slow down. So the first thing that happens is the star starts to expand, because if all this fusion that happens with all these atoms, and they're growing, the atoms are growing and growing and growing and growing because they're getting bigger and bigger atoms. So the star basically inflates into a really big star that's not quite as bright, because the fusion is starting to slow down. But they're still happening. It's creating bigger and bigger atoms, so there's still fusion happening, but it's going at a slower rate, and it's less powerful. So it's less, intense. And so you start to produce red giants. So these stars, they become red giants. They basically inflate because the fusion starts to slow down, like I said, and because the fusion starts to slow down, like I said, so they inflate and become less dense, and the red, remember, is a very high wavelength, low energy type of star. Then the death of a star, like I said, the death of a star basically happens again. So you have all these elements out here on the outside of a star that are the lighter elements, and they kind of stopped fusing because there's less gravity now. They're farther out from the surface. There's less gravity on the surface because they're really far out. Remember, r squared, so they're really far out, so there's not as much gravity pushing them together, so the density is very small out there. So there's not enough gravity out there to hold them onto the planet anymore, the planet star. So like inside the core, you still have a lot of fusion happening, and it's a lot like it's really dense in the core, but on the outside it's very gassy and very low density. So these just kind of leave. Like all these random elements just kind of leave on the outside, leaving just the core behind. And the core becomes a white dwarf. The core is basically a a white hot little star that's not very big. And there's still fusion and stuff happening with those stars, but they're just so small that, a lot of the luminosity, the power, is gone because you lost all this stuff that just kind of left because of gravity this week. So eventually the red giants will fall down and become white dwarfs. And then at some point, those white dwarfs will stop fusing, and then it's just be like a rock out in space. The death of a star. So this could take a very long time for the cycle of a star to occur. There is the life of a star. So hopefully it wasn't. Hopefully it didn't space out on this one.